All right, so today we're going to be talking about complex power. Um, so I want to give you guys fair warning that I'm going to hit you with an aggressive amount of relationships today in this particular lecture. All of them will be available to you on your equation sheet for exam 3. The equation sheet has been uploaded to Canvas for what it's worth. But I'm also going to try to convince you that realistically, you don't need to memorize or even use your equation sheet for the overwhelming majority of these relationships if you know how to use your calculator correctly. Okay. So in the video that I had you guys watch for Monday's class meeting, you learned that the average power absorbed by a circuit element is given by the relationship 1/2 Vm Im cosine theta V minus theta I. Okay. Shortly after that portion of the lecture, we then talked about effective values for periodic signals. And I believe that I derived the effective value of a sinusoidal signal for you guys. So what we could do with this relationship for average power is we could actually kind of distribute that factor of 1/2 as follows. So I could say that I have Vm divided by the square root of 2 multiplied by Im divided by the square root of 2 times the cosine of theta V minus theta I. And if we have a sinusoidal system, then Vm over the square root of 2 is just the effective value for our sinusoidal voltage. Im over the square root of 2 is just the effective value for our sinusoidal current. And then we're just going to multiply that by, once again, the cosine of theta V minus theta I. So this is what our average power relationship would look like using effective values. Okay. So some people much, much smarter than me noticed that this result for average power, where we're using effective values, is the real part of a complex number calculation. Okay. So this is the real part of the following mathematical operation. I'm going to have what I'm going to call an RMS phasor voltage. So it's different than our regular phasor voltage, which is why I've put a squiggle over the top of it as opposed to the bar, times the complex conjugate of our RMS phasor current. So now I want to show you where those RMS phasor voltage signals and RMS phasor current signals come from, right? So we know that for a voltage signal, V of t of the form Vm cosine omega t plus theta V, or a sinusoidal current waveform of the form Im cosine omega t plus theta I, these are our time domain versions of the signal. And we learned that in the frequency domain, we could represent that voltage as a phasor. V is equal to Vm angle theta V, and we could represent that current as a phasor Im angle theta I, right? So these are our frequency domain relationships. Well, what we're going to do is we're going to go one step further and convert these frequency domain signals into RMS phasor domain signals. Okay. So our RMS phasor domain voltage is literally just our phasor voltage divided by the square root of 2, because we know that the RMS value, or the effective value of a sinusoidal signal, is just the magnitude of that guy divided by the square root of 2. And whenever we divide a polar form complex number by the square root of 2, the only thing that's going to change is the magnitude. The phase angle is going to stay exactly the same. So essentially, this is just Vm angle theta v over root 2, which is just Vm over root 2, keeping that same angle theta v, or V effective angle theta v. And we could do the exact same thing with our currents. Like so. So this simple mathematical operation, actually, let me put it over here. I'm going to say that S with a bar over it is going to be equal to our RMS phasor voltage times the complex conjugate of our RMS phasor current. Okay. So this quantity right here, S, is more commonly referred to as our complex power. Okay. So complex power is just an artificial construct that electrical engineers have created to describe what's going on in a steady state sinusoidal system. Okay. It is, I hope inherently, or I hope you guys can see this, it is inherently a complex number, and buried inside of the multiple different forms of complex numbers, specifically the rectangular form of a complex number and the polar form of a complex number, is really all of the different pieces of information that we could ever need to know about how things are behaving in a sinusoidally oscillating system. Okay. So before we break this down into its rectangular and polar form parts, I'm going to ask you guys a question here, and it is 100% a trick question, okay? What do you think the units of complex power should be? So I'm multiplying voltage by current. Every other time we've done that, what have the units been?
Watts.
Watts, okay? So the units of complex power are not watts simply because it would be confusing, okay? And I know you're telling yourself, well, how the hell is it less confusing to just all of a sudden change the units, okay? So electrical engineers needed to be able to differentiate between the different parts of complex power. And so to do that, we gave each of the individual components of complex power their own units, okay? So complex power is measured in what are called volt amperes, okay? So it's literally dimensionally the exact same thing as a watt because it is a volt times an amp, but we call it volt amperes so that we know we're talking about complex power specifically whenever that particular unit is used, okay? So now let's expand this thing out, okay? I'm going to start with rectangular form. So if I multiply my RMS phasor voltage V times the complex conjugate of my RMS phasor current I in rectangular form, I should get V effective times I effective times the cosine of theta V minus theta I plus J times V effective I effective, the sine of theta V minus theta I, okay? Where this part right here, which is nothing more than the real part of our complex power S, is commonly referred to as the average power. And as it has been throughout this entire course, the units of average power are watts. Okay. So average power represents the portion of complex power that is capable of performing work. Another way to think about it is it's the part of complex power that is associated with resistance. Okay. So this is the part of the complex power that actually gets consumed or converted into heat by any physical system. Okay. Contrasting that, we have this imaginary part over here. So this is the imaginary part of S, and it is commonly referred to as the reactive power. And reactive power is measured in volt amperes reactive, or VARs. Okay. So complex power, anytime we're talking about complex power, we're going to use the unit of volt amperes. Anytime we're talking about average power, we're going to use the unit of watts. And anytime we're talking about reactive power, we're going to use the unit of VARs. Okay. So reactive power is, it essentially represents energy storage in our system, or temporary energy storage in our system. So it is associated with the presence of capacitors and inductors. Even though it is the imaginary part of the complex power, it is incredibly important to the health of our utility grid. In fact, without reactive power in our power systems, our grid would suffer from near constant blackouts and brownouts due to changes in demand at any given time. So the presence of reactive elements, temporary energy storage elements like inductors and capacitors, help the electric utility system to be able to ride through fluctuations in voltage when everybody gets home from work at roughly the same time and starts cooking dinner together. Or, everybody is, watching the Super Bowl and then they all get up to use the microwave to reheat their nachos or whatever at halftime. Whenever we see a sudden increase in demand, reactive power is what helps us ride through that without a blackout or something like that occurring. So even though it is quote unquote imaginary, it is incredibly important to how our grid operates. Okay. So typically speaking, the average power symbolically is expressed using the letter P. And you might, and I do this at times, see me put lower, AVG next to it. So it's average power. And then the reactive power is typically denoted by the letter capital Q. So basically, in rectangular form, our complex power is simply P plus JQ, like so. Before I move on to the polar form representation of complex power, does anybody have any questions? All right. So in polar form, our complex power would be written as V effective times I effective with an angle of theta V minus theta I, where V effective times I effective is simply the magnitude of our complex power, and that is commonly referred to as the apparent power. An apparent power is also measured in volt amperes because it is nothing more than the magnitude of that complex number. Okay. So the only way to really know whether you're talking about apparent power versus complex power is if you're talking about apparent power, there is no phase angle associated with it. It's just the magnitude. So if you have a magnitude and a phase angle, you have complex power. Magnitude only is apparent power. Apparent power is what power systems engineers design to, because it is essentially kind of like a worst case scenario, in as much as there's no way for phase to be taken into account that might lower quantities. So I understand that I'm talking to ostensibly a bunch of sophomores and stuff like that. So you guys probably don't own your own homes or anything like that yet. Maybe some of you do. I don't know. But I'd be willing to bet that the number of you that has ever tried to size a generator or anything like that for your home is probably close to zero. Something that you guys may have done, though, is maybe try to purchase a UPS or something like that, an uninterruptible power supply for maybe your computer, or I don't know if you're like me and have sleep apnea, something to make sure that your, CPAP stays on overnight, even if your power goes out. But whenever you try to spec out something like that, like a generator or a UPS, it'll usually have two things listed on it. It'll say something like 1800 watts slash 2100 VA. That 2100 VA is the apparent power rating for the system. Okay. So for those of you that go into internships that work at electrical utilities or even manufacturing plants and stuff like that, you're going to use your volt ampere ratings to do all of your panel schedules to figure out what size conductors that you should be using for a given system. All of that is based off of your apparent power ratings. Okay. The last part here, this angle, is commonly given the symbol theta S, and it is what's known as our power factor angle. Okay. Usually measured in degrees, although there's nothing stopping us from expressing it in radians or anything like that. And the power factor angle is related to the kind of electrical efficiency of a system. And we'll talk about that more in a little bit today. Okay. So in polar form, our complex power is simply our apparent power with an angle of our power factor angle. Okay. So I've given you guys, let's see, I've got my basic mathematical relationship V times I conjugate. Then I gave you an equation for average power, equation for reactive power, an equation for apparent power, and an equation for power factor angle. So it seems like I've just hit you guys with 5 different equations, okay? And I totally have, but realistically, we don't have to remember literally any of them except for this guy right here. If we can remember S is equal to V times I conjugate, we can get any other part of stuff just by using our calculator and remembering which part of our answer corresponds to which part of the power. So I want to explain what I mean by that by working an example with you guys. So let's say that I have the following circuit, and it's already given to you all in the RMS phasor domain. So let's say that this is 120 angle 0 degrees, volts RMS. And then I have some impedance here. Let's call it ZA. Some impedance here will be ZB. And some impedance over here will be ZC. Let's say that ZA is equal to 10 plus J3 ohms. ZB is equal to 18 angle 20 degrees ohms. And ZC is equal to 6 angle minus 45 degrees ohms. What I'm interested in us finding is, let's say, the average power absorbed by impedance ZA, the apparent power absorbed by impedance ZB, and the reactive power absorbed by impedance ZC. Instead of calculating any of those directly, what I'm going to do, and what I highly suggest you guys do, is just calculate the complex power and then take from the complex power whatever piece it is that you're interested in. Okay. So for us to calculate the complex power absorbed by impedance ZA, we would need to know the RMS phasor voltage across VA, as well as the RMS phasor current flowing through ZA. Similarly, for us to calculate the complex power absorbed by impedance ZB, we would need to know the RMS phasor voltage across ZB and the RMS phasor current flowing through ZB. And similarly, to figure out what's going on with ZC, we need the voltage drop across it and the current flowing through it. So does anybody have any thoughts on how we might determine any of those pieces of information? Trevor, sorry, this one should be IB. Thank you for pointing that out. And then Colin, I'm not sure what you mean by REZ of the circuit. So use ZEQ to find IA. Okay, so that's one way we could do it, Molly. Thank you for the suggestion. Jaime suggests that we could do voltage division to find VA. That's also a perfectly acceptable way to do it. I'm going to use ZEQ just because Molly made her suggestion first. Okay. So to me, ZEQ for this guy looks like ZA plus ZB in parallel with ZC. So that's going to be ZB times ZC over ZB plus ZC. And I'm just going to throw that into my calculator really quickly. So let's see. 10 plus 3i. I'm going to store that as A. 18 angle 20. Store that as B. 6 angle minus 45. Store that as C. And then I'm going to have A plus B times C over B plus C. And so I get an equivalent impedance of 14.402 with an angle of 1.771 degrees ohms in polar form, or 14.395 with an angle, plus J 0.445 ohms in rectangular form. And I'm going to store this in my calculator as T, for what it's worth. Good. All right. So Molly is correct that we can use our equivalent impedance to find IA. So the current IA is going to be nothing more than our source voltage, which is 120 angle 0 degrees volts RMS, divided by our equivalent impedance. So 120 over what I have stored in my calculator as T, I get 8.332 with an angle of minus 1.771 degrees amps RMS. And then using Ohm's law, I could say that VA is nothing more than, let's say, IA times ZA. So let's see. I got 86.989 with an angle of 14.928 degrees volts RMS. And from this, the complex power absorbed by element A is VA times IA conjugate. So that's going to look like 86.989 with an angle of 14.928 degrees volts RMS times 8.332 with an angle of 1.771 degrees amps RMS. So I got 724.802 with an angle of 16.699 degrees volt amperes, or 694.234 plus J 208.270 volt ampere. All right, so Colin asked in the chat, did I take the conjugate of IA? I absolutely did, because we can see right here that there's a negative sign in front of the angle for IA, and the conjugate operation in polar form simply switches the sign, which is why there is not a minus sign here, because negative 1.771 degrees is positive 1.771 degrees. So I did indeed take the conjugate, and I just used my calculator to actually do it for me because I am lazy. But I wanted to write it down to make sure that you guys caught that, so great job. So before we get into figuring out which part of this thing that we need, did anybody get any answers that were different than mine, or does anybody have any questions about anything that I did? Okay, so in the problem statement, essentially, we were asked to find the average power absorbed by impedance ZA. So which of these four numbers that I have written down for SA is the average power?
Is it the 694.234?
That's exactly right, Wes. Thank you for that. So this part right here is indeed the average power. So PA would just be 694.234 watts. So at no point did I use the equation that I gave you guys to calculate average power, because it's pointless. Our calculator can do that for us. We just need to remember that the real part of complex power is average power. So now let's work on part B, okay? So knowing what we know, how might we find either VB or IB? Because once we know one, we can just use Ohm's law to find the other.
Can we do current division to find IB?
We could, but I'm lazy, so I'm going to do it a different way. Okay. Since we know what VA is, I believe that VB is just going to be VS minus VA, right? So 120 angle 0 minus the answer that we already got for VA. There's nothing remotely wrong with using current division. You'll get the same result as I do when we get there. But that's just more crap than I want to type into my calculator, and I'm all about being lazy. So I am suggesting here, correctly, for what it's worth, that VB is just going to be 120 angle 0 degrees volts RMS minus VA, which is just the result of us applying Kirchhoff's voltage law around the left-hand loop, okay? So 120 minus what I have in my calculator as Y I get a voltage of 42.3595. So let's call that 360 with an angle of negative 31.939 degrees, volts RMS. And then IB is just going to be VB divided by ZB, which I got to be 2.353 with an angle of negative 51.9395. So let's call that 940 degrees amps RMS. So from here, our complex power is just VB times IB conjugate. So that's going to be that 42.360 angle negative 31.939 degrees volts times 2.353 angle positive 51.940 degrees amps. And I got 99.6849, so let's call that 685 with an angle of 20 degrees volt amperes in polar form. And 93.673 plus J 34.094. Sorry, there shouldn't be a degree sign there because this is in rectangular. Erase. There we go. In rectangular form. So before we figure out which part of this we need, does anybody have any questions about the analysis that I did or any of the numbers that I got? So did anybody notice that the angle of our complex power is the exact same thing as the angle of our impedance, meaning that the angle of SB is 20 degrees and the angle of ZB is also 20 degrees. Anybody notice that? So nobody's saying anything, but for what it's worth, that's a pretty good sanity check to make sure that you've done things correctly if you are given a quantity in polar form, because the angle of our complex power is theta v minus theta I, and that is the exact same thing as how we define the angle of our impedance Z, okay? So if you somehow got different angles for the impedance and the complex power, you must have made a mistake somewhere, okay? All right, so we were asked to find the apparent power absorbed by impedance ZB. So which of these four numbers is the apparent power? The 99.685. Absolutely right. So is 99.685 volt amperes. Okay. So lastly, we need to figure out what's going on with impedance ZC. So I hope that we can all agree that the voltage drop across impedance ZB and the voltage drop across impedance ZC are the same thing because those two elements are in parallel. So we can say that VC is simply the same thing as VB, which is just that 42.360 with an angle of negative 31.939 degrees volts RMS. From this, IC is just going to be VC over ZC. Which I got to be 7.0599. So let's call that 7.060 with an angle of 13.060 degrees. And I would appreciate it if you guys could throw these numbers into your calculator and tell me what you get in both rectangular form and polar form.
Rectangular, I get 282.973, minus 96.768.
That is very much different from what I got.
All right. 42,
I got for polar form, I got 299.062 angle negative 45.
So 299.062 angle negative 45 degrees. So that is not close, or sorry, it's not exactly what I got because I stored stuff in my calculator, so I wouldn't have rounding error, but it is incredibly close. So I believe that to be correct.
And then I got 211.472 minus 211.465 or J 211.465.
Yeah. Okay. So again, not exactly what I got, but very, very close just because of that rounding error. For what it's worth, whenever you have an angle of 45 degrees, the real and the imaginary parts are equal. And whenever you have an angle of negative 45 degrees, the real and the imaginary parts are equal, but they're of opposite signs. So just the imaginary part should be negative. But, 0.472 is close enough to 0.465 for me. So those both seem legit. So if we were looking for the reactive power absorbed by impedance ZC, which of these four numbers would that be?
The J number.
Yep. So it's just going to be the minus 211.465 volt amperes. Actually, volt amperes reactive, since we're talking about reactive power specifically. What do you think it means that our reactive power here is negative? So let's scroll up here and let's look at our original diagram, right? So I have the current IC is flowing out of the negative polarity terminal, or another way to put that would be flowing in to the the positive polarity terminal. So the complex power that we calculated was the complex power absorbed by impedance ZC. So because we got a negative number for our reactive power, that means that this element is supplying reactive power. So it's obeying the exact same rules that we talked about when we had just simple DC circuits. If we calculate absorbed power and we get a negative result, it just means supplied. Okay. What we'll see here in a little bit is that realistically, that just means that there's some capacitance as part of that impedance, which should make sense because we have a negative phase angle. Okay, so the next thing that I want to talk about with you guys, and this is going to be real quick, is just a graphical way to represent complex power. And this is what's commonly referred to as a power triangle. So the horizontal axis is going to be our real axis, and the vertical axis will be our imaginary axis. So if we have some complex power vector S, like so, the projection of S onto the real axis is our average power. The projection of S onto our imaginary axis is our reactive power. The length of this vector S is our apparent power, and the angle formed between the real axis and our vector is our power factor angle, theta S. Okay. So this is just a simple visual representation of the relationships that we already learned about. And effectively, it's what we're having our calculator do for us, right? So instead of using those several equations that we were given earlier, we can just say that our complex power S is P plus JQ in rectangular form, or magnitude of S angle theta S in polar form. So this is just another way to think about which part of complex power represents which thing. So if you can remember that the average power is the real part, then put your answer in rectangular form and just look at the real part. Reactive power is the imaginary part, so put your answer in rectangular form and look at the bit with the J. Apparent power is just the magnitude, so put your answer in polar form and look at the number in front of the angle sign. Power factor angle is just the part of the polar form after the angle sign, right? That's all it is. So once again, power triangle is just a graphical way to reinforce what we've already talked about. Okay, so now there are two different things that I could talk about right now. I'm going to wind up talking about both of them today. I'm trying to decide if I want to talk about power factor first or alternative relationships for complex power first. I think I'm going to do the alternative relationships first today. So, excuse me. All we're going to do with this part is see if we can simplify things a little bit further. And so all of the relationships that I'm about to derive for you guys, and this won't take but a minute or two, are based on two things. The first of which is just our basic definition for complex power. S is equal to RMS phasor voltage times the conjugate of RMS phasor current. And then the other part is just going to be Ohm's law in the RMS phasor domain. And I hope you all can see pretty easily that Ohm's law in the RMS phasor domain should just be RMS phasor voltage is equal to RMS phasor current times impedance, right? So it's the exact same thing as Ohm's law in the regular frequency domain. We just put the squiggles on top of both V and I, and we can get away with that because V with a bar over it is just V with a squiggle over it times square root of 2, and I with a bar over it is just I with a squiggle over it times square root of 2. So there's just the same factor of root 2 on both sides. So those guys cancel out, and once again, Ohm's law just looks like Ohm's law. For what it's worth, I could also write this as I is equal to V over Z. So let's start with putting everything in terms of voltage, right? So my RMS phasor voltage is going to stay my RMS phasor voltage. And now I'm going to replace I conjugate with that right-hand expression of Ohm's law, right? So I is V over Z, and then I'm just going to conjugate that guy. Well, conjugating a ratio of complex numbers is the same thing as me conjugating the numerator and conjugating the denominator. So this is going to look like V conjugate times V divided by Z conjugate. Now, if any of you have your notes handy from when we talked about complex numbers, gosh, this would have been about 2 weeks ago at this point. Does anybody remember what happens when I multiply a complex number by its conjugate? So I do wind up just getting a real number, but I get a very specific real number. Well, I don't want to, I'll just show you guys really quickly. So this is a quick aside. I'm going to wind up erasing it here in a moment. But let's say that I have the complex number 5 angle 15 degrees, and I multiply it by 5 angle minus 15 degrees, right? These two numbers are complex conjugates of each other because they have the same magnitude, but they have opposite angles. So what happens when I multiply those two numbers together? Literally throw that in your calculator if you feel like it. Tell me what the result is. So the result is indeed 25. So that 25 is important because it's just 5 squared, where 5 is the magnitude of both of those complex numbers, okay? So essentially, what I'm getting at here, and what I believe I mentioned when we did our review of complex numbers, is that anytime I multiply a complex number by its own complex conjugate, the result is just the magnitude of that complex number squared. So that means that we could express our complex power as the magnitude of the voltage drop across our element or network of interest squared divided by the conjugate of our impedance. Following a similar thing here, I could say that V is equal to I times Z. Multiplying this by I conjugate gives me I conjugate times I times Z, which is just the magnitude of our current squared multiplied by our impedance. So if we go back to that previous example problem that we worked, we really did twice as much work as we needed to using these alternative relationships, right? So let's just check this out for one thing really quickly, okay? So if I wanted to calculate SA using our alternative relationship, that would be the magnitude of VA squared divided by ZA conjugate. So that would be 86.989 volts RMS squared divided by, let me scroll up here, 10 plus J3 conjugate is going to be 10 minus J3 ohms. Well, if I throw that into my calculator, I wound up getting 724.795 with an angle of 16.699 degrees volt amperes. So the exact same result as I got, but I didn't have to go through the extra step of finding the current or anything like that. Or I guess in that particular one, I found the current first, then used the current to find the voltage, but you guys get the gist. We can get the exact same result with less information, so it's not as tedious of a calculation to perform. You can't go wrong if you use S is equal to V times I conjugate for everything. I'm just trying to show you a slightly faster way to get the same result. Okay. All right. So before we move on to the concept of power factor, does anybody have any questions?
You did say that there was going to be a formula sheet for this test, correct?
Yes. So actually, let me pull it up on Canvas really quickly. All the way down to the bottom. There we go. So it should be the last thing that is currently available on Canvas. Just says Engineering 221, Exam 3 equation sheet. It will be embedded into your exam. So probably every, let's say 4 or 5 questions, I'll just put another copy of it so that you don't have to scroll super far to find it, because I haven't figured out a way to just make it show up, like make the question show up on the left-hand side of the page and make the equation sheet show up on the right-hand side of the page. So I'm just going to put it on there multiple times so that you guys can access it pretty easily. But this is what the equation sheet has in it. So the trig identities that I expect you to know. So to go from sine to cosine, you subtract 90 degrees from your phase angle. To go from negative cosine to positive cosine, you add or subtract 180 degrees. It does not matter. Here is our definition of angular frequency in terms of linear frequency. angular frequency in terms of period, and then the relationship between frequency and period. Here we have the impedance of a resistor, the impedance of an inductor, and the impedance of a capacitor. These two representations are equivalent to each other. Then we have instantaneous power equation for a generic element, average power for the generic element. It is just the DC part of that instantaneous power relationship. Then we have our instantaneous power for resistors in terms of only voltage, instantaneous power for resistors in terms of only current, average power, same thing. Instantaneous power for inductors in terms of voltage, instantaneous power for inductor in terms of current. Same kind of thing going on for capacitors. Here's our equation to determine the effective or RMS value of a generic periodic signal. Here is specifically the effective value is just the magnitude of the sinusoid over √2 for a sinusoidal signal. Here's our complex power relationships. So this is what we talked about towards the beginning of class in rectangular form. Here's polar form, and then here's the simplified P plus JQ is equal to apparent power angle, power factor angle. Then I even remind you, average power is the real part of complex power. Reactive power is the imaginary part of complex power. Apparent power is just the magnitude of complex power. And then we're getting into power factor relationships that we're about to talk about. Here are the alternative relationships that we just derived. And then this equation right here, we're going to learn about on Friday. So it has pretty much everything power related that we've talked about for the last couple of class meetings on to the end of the class on Friday. It's got the trig identities that I expect you to be able to apply on your exam. And then I also went ahead and just gave you definition for omega period and frequency and all of that kind of stuff. And then impedances, just in case somehow you manage to forget those when you take the test. Any questions about the equation sheet before we get back to the lecture? All right. Okay, so now we're going to talk about power factor. So mathematically, our power factor is simply the ratio of our average power to our apparent power. And if we scrolled up and looked at it, or if you look at the equation sheet that we just looked at a moment ago, you would see that if I divide my average power by my apparent power, the only thing that I have left is the cosine of my power factor angle, okay? So I would say 90-ish% of the time when you're calculating power factor, you're literally just going to do the cosine of the power factor angle, okay? So let's talk about what power factor actually is here, okay? So I mentioned this slightly earlier, but it is a measure of the electrical efficiency of a system. So I would like to explain that in a little bit more detail right now. When we pay our electrical utility bill, essentially what we are paying for is the average power that we consume over the duration of the billing cycle, right? So if you took your energy usage in kilowatt hours for a month and you divided it by the total number of hours in that month, you would literally have the average power that you consume, okay? The apparent power is, in essence, what the electricity utility or the electrical utility pays to generate, okay? So the utility wants the average power to be as close to the apparent power as possible. That way, they can bill you for everything that they had to pay to generate. And by pay to generate, I mean specifically things like the cost of coal or natural gas, but also the cost of the infrastructure that is needed to deliver power from the generation station to the end consumer and stuff like that, right? So average power is what we pay for as consumers. Apparent power is what the utility pays for to produce, okay? So if that number is, or if that ratio is 1, then essentially all of the power that's being generated is being consumed by the end user, okay? And if that ratio is 0, then all of the power that the utility paid to generate is getting sent to the user and then immediately sent back because all they have is energy storage essentially. So the closer the power factor is to 1, the more efficient from the utility standpoint the system is operating at. And the closer it is to 0, the more money they're wasting on creating power. Okay. On Friday, we're going to talk about a process called power factor correction, which is what industrial consumers do when they have large inductive loads like induction motors, synchronous machines, and stuff like that, that causes their power factor to fall beyond a certain threshold. But again, we'll talk about that kind of stuff on Friday. So knowing what the power factor for our system is actually tells us quite a lot of information about what's going on. So I'm going to kind of break this thing down by thinking about what our power factor angle is and how that relates to things. So I'm going to preface this by saying that we're only going to be considering angles between positive 90 and negative 90 degrees, okay? For angles that are larger in magnitude than 90 degrees, that means that we are absorbing negative average power, which means that we have essentially negative resistance, which we're not going to worry about that. Okay, so we're only going to concern ourselves with systems where the resistance is positive. Okay, so if theta S is exactly 90 degrees, then that means that our power factor is 0. Okay. Well, for theta S is equal to exactly 90 degrees, this means that our load is purely inductive. So that means the resistance of our load is 0 and the reactance of our load is positive. If theta S is between 0 degrees and 90 degrees, then that means our power factor is between 0 and 1. And we have an inductive load. Meaning that our resistance is positive and our reactance is positive. So I'm going to add one other thing here really quickly. We talked about this when we were talking about our frequency domain relationships for current and voltage. So whenever our load is inductive, we know that our current should lag our voltage in our system. So for this particular case, where our power factor angle is between 0 and 90 degrees, we are going to say that we have a lagging power factor because our current is lagging our voltage. Okay. This is the case that we will see in the overwhelming majority of cases. If our power factor angle is exactly 0 degrees, then our power factor is 1, also called unity power factor. And this means that our load is purely resistive. So that means R is greater than 0 and our reactance X is equal to 0. For the case where our power factor angle is between negative 90 degrees and 0 degrees, once again, our power factor is going to be between 0 and 1. But this time we're going to call it a leading power factor because our current is leading our voltage. And this means that our load is capacitive. Where R is greater than 0 and X is less than 0. And then our last case that we're going to talk about is when our angle is exactly equal to negative 90 degrees. Once again, we have a power factor of 0. And this occurs when we have a purely capacitive load. Where R is 0 and X is negative. Okay. So these are the various cases that we might have. So I just want to make sure that we're all catching what I'm throwing here. Whenever our power factor angle is between 0 and positive 90, we're operating at a lagging power factor. Whenever our angle is between 0 and negative 90, we're operating at a leading power factor. Whenever our angle is exactly plus or minus 90 degrees, we have a power factor of 0. We don't consider those to be leading or lagging. And whenever we have a power factor, whenever we have an angle of 0 degrees, we have a power factor of 1 or a unity power factor, and that is also neither leading or lagging. Okay. So you might see some problems on some of the old exams. So let me pull one up really quickly. Let's see. Let's see if I asked anything about it on this guy. I'd be willing to bet I did. Yeah. Well, this one doesn't say specifically leading or lagging or anything like that, but it's the same kind of thing. The impedance of which of the following electrical loads will have a negative phase angle. So C has a phase angle of minus 90 degrees. D has a phase angle somewhere between 0 and minus 90. And F has a phase angle somewhere between 0 and minus 90. And I can see that just by looking at them because I know what my power factor angle relationships are. Let me open up a different one really quickly. Nope, that's the exact same question. Didn't ask it on that one. Yeah, like this guy right here. Which of the following loads will operate at a lagging power factor? So based on what we just talked about, and I know that I have the correct answer highlighted, but why is B correct? Anybody care to take a stab at it? So Gustavo says in the chat that it's operating at a lagging power factor because the power factor is going to be between 0 and 1. But that's not correct because the power factor is going to be between 0 and 1 whenever we have a leading power factor as well. So it's because our resistance is positive and our inductance or our reactance is also positive. So Molly is correct because it has an inductor and a resistor, right? So element A right here is going to operate at unity power factor, which is neither leading nor lagging because it's just a resistor. C is going to operate at a power factor of 0, which is neither leading or lagging. E is going to operate at a power factor of 0 because it's neither leading or lagging. And D and F are going to operate at leading power factors because the resistance is positive and the reactance is negative. So lagging power factors always occur when we have positive resistance and inductance. Leading power factors occur when we have positive resistance and capacitance. All right. I've talked about pretty much everything that if it's, so Trevor asked, how do you know if it's unity, if it's only a resistor? Realistically, and I'm not genuinely not trying to confuse you or anything like that. But you could have inductance and capacitance in a network and it still operate at a unity power factor if the reactances canceled each other out. Meaning that if you had an inductance whose impedance looked like plus J5 in series with a capacitance whose impedance looked like minus J5, those guys cancel each other and that network as a whole will operate at a unity power factor. But I'm not going to give you anything that has both capacitance and inductance and ask you that kind of question just because I don't want to confuse anybody or make you go through that much effort. Okay. Okay. So as I said, I've talked about everything that I wanted to talk about for today, for the most part. I'd like to work, I guess, one more quick thing. So let's calculate the power factor at which the voltage source in our original circuit was operating. Okay. So I'm going to be lazy, and I hope you guys will be relatively okay with this. So I'm just taking this example right here. Same thing that we did earlier, except now what I want to know is at what power factor does the voltage source supply power? So for this particular calculation, I'm going to do what we did earlier. I'm going to calculate the complex power, and then I'm going to use the complex power in order to determine power factor. So I saved this information down here about finding ZEQ, like Molly suggested earlier, because realistically, the only thing that we need is the voltage drop across the voltage source, which is given to us, and then the current flowing through the voltage source, which we can calculate from ZEQ. We calculated it earlier, but just to remind you, the current IA that's flowing into the negative polarity terminal is just going to be 120 angle 0 degrees volts RMS over ZEQ. And so that would be, I think I still have the stuff saved in my calculator. 8.332 with an angle of minus 1.771 degrees amps RMS. So the complex power supplied by our voltage source is just going to be Vs, sorry, that should have a squiggle over it, times IA conjugate, because we're calculating supplied power, and that current is flowing into the negative polarity terminal, out the positive polarity terminal. So that's just going to look like 120 angle 0 degrees volts RMS times 8.332 with an angle of positive 1.771 degrees amps RMS. And so when I multiply that together, I get 999.848 with an angle of 1.771 degrees volt amperes. So my question to you guys is, from this information, how do I calculate my power factor?
Is it not just the cosine of the angle?
That is exactly correct, West. It is literally that easy. So cosine of 1.771 degrees which I got to be 0.99952. Who can tell me if that power factor is leading or lagging?
Lagging?
Colin says it's lagging. Would you care to justify that answer? It is correct, by the way.
Angles in between 0 and 90 degrees.
Yeah, so if the angle's positive, it's a lagging power factor. If the angle's negative, it's a leading power factor. It is literally that simple. So this particular system, just by random chance, because I've made those numbers up, is operating extremely closely to a unity power factor, okay? Will we ever get an angle above 90 degrees? Trevor, we will not, because an angle above 90 degrees means that we are dealing with negative resistance. So, like if you calculated the power absorbed by this voltage source, you would wind up getting an angle that's larger than 90 degrees because we're simply looking at it kind of in the wrong direction, right? So we've got a source supplying power to those three impedances, if we treat the source as if it's absorbing power, it's going to wind up having an angle that's greater than 90 degrees just because of the way that the math works out. But that really is just meaning that we've considered our powers flowing in the wrong direction. So I won't ever ask any questions on your exams, homeworks, or anything like that to where you'll get an angle that is greater in magnitude than 90 degrees, because I don't want to confuse you guys. All right, I think I'm actually done harassing you guys about complex power for today. I will still hang out on Zoom if anybody has any questions about anything. I'd be happy to answer them. Could be related to what we talked about today or what we talked about last Monday, since you guys just watched the video and didn't have an opportunity to ask any questions. I can answer questions about any of the take-home exams, or not the take-home exams, the practice exams, just whatever you want. If you've got questions, I'm here. Please ask them. If you don't have any questions, have a great rest of your day.